Hello, learners. Have you ever used Excel to keep track of expenses, calculate sales, or manage data from different locations? Well, what if I told you were already using matrix operations without even realizing it? Matrix operations help us model and solve real world problems that involve structured data, like quantities produced in factories, prices across markets, or resource allocation in logistics. Take this scenario. Suppose two factories produce three types of items: tables, chairs, and shelves, and you want to find the total production of each item. You can represent the production as two matrices, one for each factory, and simply add them to get the total output. These operations aren't just theoretical, they're used in economics, computer graphics, machine learning, and engineering. So, before we dive into formulas, let's explore the foundational matrix operations: addition, scalar multiplication, subtraction, and of course, matrix multiplication. Alright, let's begin with matrix addition. If you've ever added two data tables with the same layout, you already know the rule. Matrix addition is only possible when both matrices are of the same order, meaning they have the same number of rows and columns. We add them element-wise, which means each element in position ij of matrix A is added to the element in the same position ij of matrix B. Mathematically, if A equals open bracket A sub ij close bracket and B equals open bracket B sub ij close bracket, then A plus B equals open bracket A sub ij plus B sub ij close bracket. Let's see an example. Matrix A equals first row 3, 1, negative 1. Second row 2, 3, 0. Matrix B equals first row 2, 5, 1. Second row 1, negative 2, 3. Then A plus B equals first row 5, 6, 0. Second row 3, 1, 3. Now, let's understand scalar multiplication, where we multiply every element of a matrix by a constant number called a scalar. Suppose matrix A equals first row 3, 1, 1.5. Second row 5, 7, 3. Now multiply A by the scalar 3. 3A equals first row 9, 3, 4.5. Second row 15, 21, 9. So mathematically, if A equals open bracket A sub ij close bracket, then scalar k times A equals open bracket k into A sub ij close bracket. Now, what if the scalar is negative 1? That gives us the negative of a matrix. So, negative A equals minus 1 times A. It's just the matrix with all elements sign reversed, and we use this to define subtraction or additive inverses in matrix algebra. Alright. Once you understand negative matrices, subtraction is straightforward. To subtract B from A, we write A minus B as A plus negative B. So, if A equals open bracket A sub ij close bracket and B equals open bracket B sub ij close bracket, then A minus B equals open bracket A sub ij minus B sub ij close bracket. Let's also understand some fundamental properties of matrix addition. Commutative property, A plus B equals B plus A. Associative property, within brackets A plus B plus C equals a plus within brackets B plus C. Identity element, A plus 0 matrix equals A. Inverse element, A plus negative A equals 0. Matrix just like numbers, matrices follow these familiar rules, but only if the matrices involved are of the same order. Now let's look at how scalar multiplication interacts with addition. If you have a scalar k and two matrices, A and B of the same order, then k times within brackets A plus B equals Ka plus Kb. That's called distributivity over matrix addition. Another rule is, if you have two scalars K and L, then within brackets K plus L times A equals Ka plus La. These distributive properties are super helpful when simplifying long algebraic matrix expressions. And the best part? They work element by element, meaning they are consistent with basic arithmetic but applied to structured data. Now comes the most powerful operation, matrix multiplication. This one's a bit trickier. Matrix multiplication is not element-wise. It is only defined when the number of columns in matrix A equals the number of rows in matrix B. To compute an element in the product matrix sub, say the element in row I and column K, you take the ith row of A and the kth column of B and do a dot product, meaning multiply corresponding elements and sum them. Mathematically, C sub ik equals the summation over j of A sub ij times B sub jk. Here's a quick example. Matrix A equals first row 1, 1, 2. Second row 0, 3, 4. Matrix B equals first column 2, 1, 5. Second column 7, 1, 4. Then AB equals first row 13, 2. Second row 17, 13. It's a neat way to combine row data with column data to produce something entirely new and useful. Let's remember a few important rules about matrix multiplication. It is not commutative. That means A times B is usually not equal to B times A, even if both products are defined. Also, if A times B equals 0 matrix, it doesn't mean either A or B is 0. That's different from ordinary arithmetic. But there is an identity matrix I such that A times I equals I times A equals A only for square matrices. Other algebraic properties include associativity, A times within brackets B times C equals within brackets A times B times C left distributivity, A times within brackets B plus C equals AB plus AC right distributivity, within brackets A plus B times C equals AC plus BC. These are powerful tools when simplifying matrix equations or solving real-world problems. Let's quickly wrap up what we learned. Matrix addition and subtraction are done element by element and require matrices of the same shape. Scalar multiplication scales each element in the matrix, stretching or shrinking the entire data grid. Matrix multiplication, though more complex, is a structured way of combining rows and columns to derive meaningful relationships. All these operations follow logical rules, just like regular algebra, and are used in fields like data science, network analysis, computer graphics, and engineering modeling. And that's the foundation of how we work with matrix operations in mathematics. Stay curious, and I'll see you in the next lesson.